Welcome. Today we're going to crack open one of the most powerful tools in all of mathematics, the integral. If you've ever wondered how we can possibly measure something that's constantly changing, well, you are in exactly the right place. Let's dive in.
So let's kick things off with a pretty basic question. We all know how to find the area of a square, right? You know, length times width. Easy enough. But what about a shape with curved edges? Like this one. All of a sudden, those simple formulas just don't work. So, how do we solve this?
You know, this question, which seems so simple, actually stumped mathematicians for centuries. It required a total shift in thinking, a completely new way to look at shapes and space.
Yeah, think about it. On one hand, you've got a rectangle. It's predictable, it's easy. On the other hand, you have a curve. It's fluid, it's always changing, and that makes pinning down its exact area a real puzzle.
So how in the world did they solve this puzzle? Well, the answer is just beautifully simple. Instead of trying to measure the whole thing at once, the big breakthrough was to ask, what if we just sliced it up into an infinite number of teeny, tiny, manageable pieces?
And that, right there, is the core idea behind integration. It's really just a tool for adding up a mind-boggling number of tiny little parts to get the whole picture. You could call it the ultimate divide-and-conquer strategy in all of math.
Okay, let's actually see how this works. Imagine we try to fill in the area under our curve using just a few big, wide rectangles. And as you can see, it's a pretty rough fit, right? You've got these big gaps, some parts are sticking out, it's just not very accurate.
Okay, but now, what if we use way more rectangles and we make each one super thin? Look at that. The approximation gets so much better. These rectangles are starting to really hug the curve, and those gaps, they're getting smaller and smaller.
All right, now let's take this idea all the way to its logical conclusion. What if those rectangles became infinitely thin? I mean, so thin, they're basically just lines. They would perfectly fill that entire area, no gaps whatsoever. And that perfect sum, that is exactly what an integral gives you.
Okay, here's something really important to remember. When we think of area, like the area of a room, it's always positive, right? But an integral, it calculates what we call signed area. This just means that any part of the shape that dips below the x-axis, the integral is going to count that as a negative number. So to get the actual physical area, we just have to take the absolute value. Basically, just make those negative parts positive before we add everything up.
All right, so we've got the why down. We understand the big idea. Now let's get into the how. Let's start building our calculus toolkit with the actual formulas you're going to need to calculate these things.
And what's super cool here is that you actually have options. You can slice things up vertically. That's what we call integrating with respect to x. Or you can slice them horizontally, integrating with respect to y. And honestly, depending on the curve you're dealing with, one way can be way easier than the other.
Okay, so that's great for finding the area between a curve and an axis. But what about something a little more complex? What if the area you're trying to find is actually trapped between two different curves?
Well, the concept here is actually surprisingly simple. Basically, you find the area under the top curve. Then you find the area under the bottom curve, and you just subtract it. The trick, and this is the most important first step, is to figure out exactly where those two curves intersect, because those points, those are your start and end points for the integral.
Okay, now for the fun part. Let's talk about some pro tips and shortcuts. Seriously, these are the kinds of tricks that can save you a ton of time, especially if you're in an exam situation.
Okay, this one is a real game changer. If you can see that your shape is perfectly symmetrical, why would you do all the work twice? Just find the area of 1/2 and then double it. Boom, you're done. It's way faster and you've got less chance of making a silly calculation mistake.
And here's another great one. You'll find that some combinations of curves show up all the time, so often that people have already figured out their areas. Memorizing just a few of these, like the area of an ellipse or between a line and a parabola, it's almost like knowing the answer to the test before you even start.
Okay, theory is one thing, but let's actually put this into practice. We're going to take everything we've just talked about and walk through a classic problem, step by step.
So here's the problem. Find the area of that little region that's enclosed between the line y equals x and the parabola y equals x squared. So to do this, we're going to follow a simple 5-step plan. Think of this as our foolproof roadmap to the solution. First, sketch it out. Then, find where they cross. Figure out which curve is on top. Set up your integral, and finally, solve it.
Okay, step 2 and 3, we got to find our limits and which curve is on top. To find the limits, we just set the two equations equal to each other, x equals x squared. And when you solve that, you find they cross at x equals 0 and x equals 1. Now, which curve is on top? Well, let's just pick a number in between 0 and 1. How about 0.5? For the line y equals x, you get 0.5. For the parabola y equals x squared, you get 0.25. So yep, the straight line is our upper curve in that region.
All right, time for step 4. Let's set up that integral. We already know our limits. We're going from 0 to 1. And the thing we're actually integrating is just the upper curve minus the lower curve. So that's x minus x squared. Now for the magic of calculus. We find the antiderivative of that expression. For x, that becomes x squared over 2. And for x squared, it becomes x cubed over 3. And that's the expression we'll use to get our final number.
And now for the final step. We plug in our limits, 1 and 0, do the subtraction, and what do we get? The area of that little impossible-to-measure shape is exactly 1/6 of a square unit. How cool is that? It's just so clean, precise, and powerful.
So, we did it. We measured the area of a curvy shape. But the real takeaway here is this bigger idea, breaking down a complex problem into infinite tiny pieces to understand the whole. It's an idea that's used everywhere, from physics and engineering to economics and computer graphics. And that kind of leaves us with a final, bigger question. What other seemingly impossible problems out there could you solve just by learning to think in infinite slices?